So in our last video, we started talking about curvilinear motion, which is motion along some kind of curve. And we talked about the basic format where you usually have some vectors. You're working with vector analysis, trying to relate these position, velocity, and acceleration as they are all derivatives of each other with respect to time. Relating these so that we can find motion that is happening along a curve. And in our last video, we did that with rectangular components in X, Y, and Z, but that's not the only way we can do it. One other really popular, really good way to analyze these problems is through something called normal and tangential components. So normal and tangential components are really, really useful to use when you know the path of travel. So when the path of travel is known, this is a really, really good time to use these normal and tangential components. And so what does this mean? What do we mean by these normal and tangential components? So if I have some curve that my particle is traveling along, say he's here, I'm going to shift my axes. So actually I'm going to rotate this a little bit just so it shows up. Actually, let me just draw this again. Draw this again so it shows up a little clearer. Yeah, let's use this one. So if I have my particle, say he's right here on my line. Instead of using the traditional X and Y axis that he's traveling along, what I'm going to do is create a coordinate system that is made up of a new axis system, where the axes are the tangential, so that's coming off of the crest of that curve, tangent to the curve. I have one axis, we'll call this the t-axis for being tangent to where that curve crests, and then a normal axis, and this is perpendicular to that tangential axis, going inwards, usually towards some center point of the curve. So if we think about this curve as kind of like a portion of a circle that's lining up, we have our particle tangent to it, and then the normal goes in towards the center of the circle, in kind of like a radius of that circle. So this is like a skewed XY almost. It gives you a normal and tangential. And in addition to this being really helpful when we have a known path, it can also be really helpful because velocity is always tangent to the path. So we may be given a known velocity, and we say, okay, the velocity is going this way, because velocity is always tangent to the path. So if you're given the magnitude of the velocity, it can be really helpful to use these tangential components. Velocity is always tangent. Whoops, why did that not show up? Sorry, tangent to path. So when we're looking at these, we still have our same relationships of position, velocity, and acceleration, but we're going to think about them a little bit differently on this skewed coordinate system. So in this case, our position, we're going to have some position S. That's really just traveling along the length of that curve. Somewhere you have that position. And we're still going to have a vector for position. Position is somewhere on the path. The path is known, so we have what this vector is usually, right? It's a known path that we're traveling most of the time for these problems. And when we take this derivative, when we take the derivative of the position to get the velocity, velocity is ds dt. You also might see it written as s dot, as in just the derivative of position with respect to time. And it's important to remember that this vector, velocity in vector form, velocity acts entirely along the t-axis there, always tangential. So we can think about this like if we have a unit vector representing the t-axis and a unit vector representing the normal axis, it's entirely in the t direction. So it's that derivative of velocity, or derivative of position with respect to time, is going to give us that velocity. Now with acceleration is where it gets a little bit more complicated, because acceleration is not just tangent to the curve. We can have acceleration in any direction, really. It is not exclusively tangent to the curve. So our acceleration is going to have components in both the tangential direction, so we're going to have a tangential acceleration in the same direction as the unit vector t. So this tangential, that again is totally in the t direction, a t component, and we're going to also have an n component. So just like when we had rectangular components, we had ax and ay, and it was ax I hat and ay j hat. Instead here we're having a in the t direction, in the unit vector of the t direction. So instead of I hat, because I is the unit vector in the x direction, now it's the unit vector in the t direction. Plus, oops, I didn't mean to be that a different color, but oh well, our, whoops, let me fix that real quick. Plus our acceleration in the normal direction, along the normal axis, times the unit vector of the normal direction. Right, so what are these terms? These are new to us. We can understand that this velocity tangent is just velocity. There's no velocity in the normal direction, but what do we do about these guys? What are these guys? These guys have defined parameters. So our tangential acceleration, as we might expect, that's where our derivative from velocity comes in, right? We only have this velocity with respect to the tangential direction, so we can take this derivative with respect to t, right? Our dv dt is going to give us our tangential acceleration. Might also see it written as v dot, or maybe even s with 2 dots if you're feeling extra spicy. And so this is one way that we can find our tangential acceleration. We can also find this tangential acceleration through way back when we learned the rectilinear relationships. The relationship of ADS equals VDV also holds true here. It holds true for our tangential acceleration. This relationship between the velocity that's only in the tangent direction has that relationship for our tangential acceleration. So tangents stay with tangents. And then we have to figure out what to do about this normal, right? What is our normal acceleration? Well, really, a normal acceleration is also called a centripetal acceleration. And an equation that we can use for that, our acceleration in the normal direction, is the magnitude of velocity squared over rho. Really, well, what is that? What does that mean? This right here, this is the Greek letter rho. And what that rho is the radius of curvature. Oop, that's not how you spell that. Radius of curvature. So what this means, this radius of curvature, is that on some curve that we have, if we pretend like this curve goes into a circle, right? The portion of this curve here matches up with a circle. The radius of curvature is the center of that circle. Rho. This is some origin point, and then as the curve changes, it may be a different circle. right? So over here, the value of rho, this radius of curvature, might be smaller. So this radius of curvature represents the radius from a fixed point, from a center point, to the curve. And this is defined, we can define this with rho equals, and I'm sorry, it's a big, long, nasty equation. It's not hard to use, it just looks kind of gross. 1 plus dy dx squared, all in the numerator to the 3/2 power, all over the absolute value of the second derivative, d squared y, d squared x, or dx squared. Absolute value of the second derivative of the relationship between x and y. So what this radius of curvature does is help us put it in the normal direction, right? This radius of curvature essentially reroutes some of that velocity, some of that relationship there, so that this is in the normal direction, right? Not the tangent. This is our AT, but what we want is a relationship in our normal direction. So let's go ahead and practice finding this radius of curvature first, and then we'll go ahead and look at a problem where it may be more beneficial to use these relationships for this normal tangential setup instead of an XYZ rectangular setup. And I know it looks a little bit confusing, it's a little bit different of a layout with these equations, but it's still, we have our position, derivative of position is velocity, derivative of velocity, again, velocity is just tangential, so derivative of velocity gives us tangential acceleration. The only new guy that we're going to have to really learn and deal with is this acceleration in the normal direction. And again, with these accelerations, their magnitude is going to work exactly like all of our other magnitudes. Square root of our tangential acceleration squared plus normal acceleration squared gives an overall magnitude for acceleration. So again, let's go ahead and look at a problem with this radius of curvature, and then look at a problem with our normal and tangential components. So let's take a minute to find radius of curvature and understand what that means through an example. So here we have somebody skiing on a slope, and we're given the equation of that portion where they're at, that relationship of their y and x location. We're given that y is 1 over 20, 1/20th times x squared. And we're given their position, they're at x equals 10 and y equals 5. That's where they are in space on that slope. And what we're going to do here is we're just going to find the radius of curvature of that curve, of that function, where they are at A. And so again, that radius of curvature formula is going to be 1 plus dy dx squared. And then all of that is going to be to the 3/2 all over the absolute value of second derivative d squared y over dx squared. So if I look here, the main ingredients that I'm going to need are those derivatives, right? I'm given the relationship between y and x. I need the derivative of y with respect to x. So if I take the derivative of y with respect to x, my function up here, I'm going to get 2 over 20, which I'll simplify to 1/10, times x. And then if I take my second derivative, so deriving this derivative, second derivative of 1/10 x is going to be just 1 over 10. It gets rid of that x when I take that derivative. So now I can go ahead and plug this into my radius of curvature formula. So rho, my radius of curvature, is going to be 1 plus dy dx squared. Y dx squared. So that's 1/10 times x. And what's my x here? It's 10. That's the location that we're at A. Our x is going to be 10. So this times 10 squared to the 3/2 over dy squared dx. So this second derivative, absolute value, 1/10. So I can simplify this guy. I get 1 plus 10 times 1/10 is 1, and that squared is 1. So I get 1 plus 1 to the 3/2 over 1/10, or I can simplify that to be 10 times 2 to the 3/2. I plug that into a calculator. It's going to give me 28.28 meters. That's the radius of curvature. So if I created a circle that was tangent to where this skier is skiing, right, the radius here from where the skier is to the center following along the normal axis, this row of that imaginary circle is 28.28 meters. So let's go ahead and take this. We're going to work a problem with this skier using this radius of curvature to understand these position, velocity, acceleration relationships in terms of tangent and normal. So still looking at our skier, we have our skier traveling at a speed of 6 meters per second when he's at point A, which is increasing at a rate of 2 meters per second squared. So we want to determine the direction of velocity with respect to the x-axis, then find the magnitude of acceleration and its direction with respect to the x-axis, and we're going to neglect the size of the skier. So when I say that sometimes these normal and tangential are a little bit easier to use, this is one of those cases, right? The velocity that's given to us, it's a little darker, brighter. This velocity that's given to us is not in terms of x or y. The velocity itself is given as the tangent of the curve. You're already given that velocity vt. It is straight up given. It is written out for us, given the velocity in the tangential direction. We don't actually know what it is in the x direction. We don't know what it is in the y direction. We only know the overall velocity as the tangent as 6 meters per second while we're at point A. And then it says that is increasing at a rate of 2 meters per second squared. So, what does that mean when we think about it? If that velocity is increasing by 2 meters per second squared, that's an acceleration. And that acceleration is only along that tangential axis. It's referring to this tangential speed. So that is our acceleration in the tangential direction that's given to us. 2 meters per second squared. And what we want to determine, we're of course also given all that information that is in the chart on the left, such as y equals 1/20 times x squared. We're given at A that x is 10 and y is 5. And then what we want to find is we want to determine the direction of velocity. So direction of velocity, direction, when we're looking for that, is going to be an angle. And we don't need to find the magnitude, right? We're already given the magnitude of velocity because velocity is vt, right? No normal component to velocity. Velocity is given, but we don't know the direction of the velocity. So we're going to find the direction of velocity, that angle, with respect to the x-axis. Then we're going to find the magnitude of the acceleration and its direction with respect to the x-axis, right? Because acceleration is not just tangential, it has both the normal and the tangential components. So our acceleration may be pointing something like this way. We don't know exactly where this acceleration is pointing. Could be anywhere there between the t-axis and the n-axis. I have no idea. And that's what we're going to do. We're going to find out. So to do this, we're going to go ahead and find our direction for velocity first. Our direction for velocity. Right, so really what we're finding here, since our velocity is entirely in the tangent, what we're trying to find is the slope of this line. Right, a slope is just a rise over run, and with that relationship we can find an angle. Right, we can essentially find a triangle for this slope. One that maybe looks a little bit better than that. So if we can find this slope of the tangent, the velocity acts totally in the tangential direction, we can find the slope of that line, we can find the direction of the velocity. If we think back to our calculus, what is a slope really? Well, a slope is just a derivative. A slope is just a derivative. So if I take the derivative of that function at point A, taking the derivative of y equals 1/20th x squared at point A, my derivative, dy dx, is going to be 1/10 x. And again, our x at point A is 10. So that's 1 over 10 times 10 gives us 1. So we have a slope of 1, right? Our derivative gives us the slope is 1. And so if we have a rise and a run of 1 over 1, a little ratio triangle here, rise over run is just 1. That's a perfect triangle. We know what that triangle is. That is a perfect 45-degree triangle. And if we didn't know that by looking at it, we could always do the arctangent of this slope. Arctangent of 1, and that's going to give us the exact same thing. That's going to give us 45 degrees. 45 degrees. So don't get it confused. It's not this 5 and 10. These guys, it's not the ratio triangle of the position of where you are. It's the slope of that velocity, right? The slope of that velocity, the derivative of that velocity is what's giving us that direction. So now that we've got that, got this guy is 45 degrees, yippee. The other thing we need to find is the acceleration and its direction. So the acceleration, remember we have two components to that. Two components to our acceleration. Acceleration is going to be square root of our tangential component squared plus our normal component squared. Tangential component we already have. They gave it to us in the problem statement. So that's fairly straightforward. The thing we don't have is this an, that normal component of the acceleration. Thankfully, we have a handy-dandy formula for that, where our normal component of this acceleration is going to be the velocity squared over the radius of curvature. Thankfully, in that last problem we did, we actually found the radius of curvature for this exact same problem, so we can use that same radius of curvature, that 28.8 that we found, or 28.28 that we found in the last problem. It remains the exact same. 28.28 meters, and our velocity was given to us as 6. So that's 6 squared, 6 meters per second squared. Sorry, 6 meters per second. All of that is squared. 6 squared over 28.8 gives us 1.27. Now that's meters per second squared. And so now that I have this guy, I can plug it in to find the magnitude of that acceleration. Acceleration is square root of 2 squared plus 1.27 squared gives us an acceleration of 2.37 meters per second squared when I pop that puppy into the calculator. Now, how do I find its direction? Right? How do I find its direction? If I have an acceleration that's going in the tangential direction over here of 2 meters per second squared, and then in the normal direction here of 1.27 meters per second squared. I'm still going to treat it just like I did with velocity, or just like I would with any kind of ratio problem. Just understanding that what I'm getting isn't in respect to the x-axis when I do this arctangent. So when I do the arctangent of these two variables that I have for n and t axes, I do the arctangent of 2 over 1.27, I'm getting 57 degrees. But again, that 57 degrees is not out from the x-axis, it's actually out from our n-axis. Right? It's offset here. So our A, here's the angle that we just found. And there's our overall A. That 57 degrees is out from the n-axis. What I need to do to get this from the x-axis, we found this angle here between our slope and the x-axis. That was our 45 degrees. We know that our angle between the slope and the normal axis is a perfect 90, because that angle between the tangent and the normal is a 90. And then finally, we found that angle of A at 57. So to get the angle from the x-axis, we need to add all of those things together. So that's going to give us an angle of 45 plus 90 plus 57, for an angle on the acceleration of 192 degrees from the x-axis. This is what we mean when we say that it can be a little bit easier to use the normal and tangential components, especially if we're given something that's already acting in the tangential direction, instead of splitting it up into x and y. Right? The x and y angles are all a little bit different, they're a little bit off, where it can be a little bit easier to use the normal and tangential. But I know it can be a little bit of a hard concept to grasp, so let's do one more example together. In this example, we have a race car traveling around a horizontal circular track that has a radius of 300 feet. Ooh, radius is given, thank goodness. We're not going to have to worry about any radius of curvature or anything, since we're given a radius and it is a perfect circle, as it says. So if the car starts from rest and increases its speed at a constant rate of 7 feet per second squared, determine the time needed to reach an acceleration of 8 feet per second squared. What is the speed at this instant? The car is going to start from rest. All right, so again, a whole lot of words that we're going to have to determine what's important in here, what can we pick out, what do these words actually mean? So what we're given here is we're given that they're on a racetrack with a radius of 300 feet. So again, that radius of 300 feet is signaling to us we can use that as a radius of curvature. If you're doing a different method that wasn't this normal tangential, it may not be as critical that we know what this R is, that we know what this radius of curvature is. But thankfully we have it. It's 300 feet. If the car starts from rest, which I see I have in here twice now, the car is starting from rest, so we'll just make a note that initial velocity here is 0, and increases its speed at a constant rate of 7 feet per second squared. So what does that mean? Increases its speed at a constant rate of 7 feet per second squared. So really what this means is that speed, again, velocity, always in the tangential direction. So if it tells us that the tangential direction speed has an acceleration, it's increasing at a constant rate of 7 feet per second squared, that's going to be our tangential acceleration. 7 feet per second squared. And we want to determine the time needed to reach an acceleration of 8 feet per second squared. I know you might be like, well, what do you mean we have this acceleration? It's constant. How are we getting to an acceleration of 8 feet per second squared? But remember, in a tangential and normal system, we have the two different directions that we're going to be in, right? So not only do we have the tangential acceleration in the direction of our velocity, we have that normal acceleration that gives us an overall together. We can find the magnitude of that to find the overall acceleration. So what this 8 is that's the overall magnitude, the acceleration. We want to find the time it takes to reach that. So initially we start from rest, we only have this tangential acceleration of 7 feet per second squared. It's increasing. And what we want to find is the time it takes to get there. Time it takes to get to that 8 feet per second squared for the overall A, not for the tangential A, which is constant. And then we also want to find the speed at that instance. So what is the velocity? Right? What is the velocity that's happening? So the first thing that we're going to want to do is see what relationships we have, right? So if I have my accelerations, I can use my tangential and my overall acceleration. I can use those things to find a normal acceleration. Because when I have a normal acceleration, let's just write out some of the definitions that we had before. So some of those formulas that we had before that we could start with any of these. Acceleration, square root of at squared plus an squared, where our at is the derivative of velocity, right? So that's our, we can call it v dot, or you can call it the derivative of v with respect to t. That's one of the relationships we had. We also had our normal acceleration. That's the magnitude of velocity squared over the radius of curvature. So what I can do is if I find out what this normal acceleration is, I can use that to plug in here. We know the radius of curvature, so I can find that velocity. Right, that's one of the things I'm going to look for. I can find that velocity. And then I'm also looking for time, so when I have a velocity and the at, I have a relationship with that in time. So let's go ahead and go through all of those things that we've just discussed. Right, we're going to find the normal acceleration first. And this is probably the most logical just because we aren't given that many things. So it makes sense to just find some things that we can find. So let's find, we have our acceleration was given. We want to find it at 8. And I'm going to go ahead and move that square root over. So 8 squared is going to equal 7 squared. That's our tangential acceleration, plus an, our normal acceleration squared. That's easy enough. I can subtract that 7 squared over. I get a normal acceleration in the normal direction of 3.87 feet per second squared. So now that I have this, I can plug it into v squared over rho, right? This normal acceleration equals v squared over rho. And I know what rho is. It's that 300 feet that was given as the radius of the racetrack. That's the radius of the curve. Radius of curvature. So my v squared is going to be 300 times 3.87. I can take the square root of that to find the magnitude of that velocity, which is going to be 34, about 34 feet per second squared. Actually, let me, whoops. There we go, that looks a little better. 34 feet per second squared. So we found our velocity. We still need to find our time. How long does it take it to accelerate up to this 8 feet per second squared? So now that we have a velocity, we know our tangential acceleration. That was a constant 7 feet per second squared for AT. We have a velocity, and we have that relationship between dv and dt. Right, so what we can do is we can rearrange this. Actually, let me not plug anything in yet. Let me rearrange this. AT is dv dt. Again, this feels just like a rectilinear kinematics problem, right? We're going to move over the dt, keep our dv there, and we're going to try to find our time. So AT, since it's constant, what we have is 7 dt equals dv, and we're going to integrate each of those. So our time, we're going to start from a time equals 0, and we don't know what time we're going to. This is what we're solving for. And then for our velocity, we were given an initial velocity condition of v naught equals 0. And then we know that final velocity condition, right? At the time of interest, the velocity is 34 feet per second. That gives us our upper bound of 34. And these might be the easiest integrals that we do in this entire class, because what we're going to get is the integral of dt is just going to be t. So 7 times t equals the integral of dv from 0 to 34 is v. V from 0 to 34 is just 34. So I divide that 7 over, and I get a time of 4.87 seconds. Right? It's a combination of a lot of these skills that we've been working with before. We're just using a little bit different coordinate system, but all of these things still interact in a very similar way. Our magnitudes are still the square roots of the squares. Our acceleration is still the derivative of velocity. It's just keeping in mind that sometimes there are some new equations. For example, this acceleration in the normal direction has its own special equation that we have to use when we're working in a different coordinate system. So just being cognizant that in the different coordinate systems, we may have different requirements, we may have a little bit different equations, but we just want to use the best coordinate system for us. Right, so in this one, the best one was this tangential, just because it made things a little bit easier to solve. So you may work in the XYZ, you may work in normal tangential, or in our next video, we're going to take a very brief look at cylindrical or polar coordinates and how those might be used to solve these curvilinear motion problems.